Okay, this is going to be a presentation on dimensional analysis. And dimensional analysis really is nothing more than the algebra of units. Dimension is a fancy name for a unit. It's a little bit more general, but never mind. Now, examples of units. In physics, we have such as meters, which is a unit of length, seconds, a unit of time, and kilogram, which is a unit of mass. These are called fundamental units. There are actually 7 in physics. There are three of them listed here, and we can combine these units to get other units. For example, we can have meters per second, which is a unit of speed. We can have meters per second squared, which is a unit of acceleration, and we can have kilograms per cubic meter, which is a unit of density. Fundamental units combine to have other units, which are called derived units, but no need to really remember that. Now, the important thing about units is they follow the same rules of algebra in terms of canceling out as any other variables in algebra, and so that makes them useful. Okay, as we will see. Now I'm going to use a number of examples in algebra to illustrate what I mean. In algebra, a rule of algebra is you take x times x and you get to x squared. Now x can be anything, but in physics we can have it have meaning. So for example, meter times a meter gives you a square meter and meter squared, and that has physical meaning. For example, if I take a rectangle that has 3 meters by 5 meters. Now remember, meter is a unit of length, but now let's take the area of this thing, okay? Now the area of a rectangle is length times width. Okay, well, the length is 5 meters times 3 meters, or the other way around. And what you get is 3 times 5. So you multiply the numbers, of course, but you also multiply the units. Okay, 3 times 5 is 15, and meters times meters is meters squared. So meter squared is a unit of area. This region represents a 15 square meters, roughly, you know, there's a square meter-ish, okay? And this region would represent 15 square meters of area, okay? All right, moving on. In algebra, we can also have something like this, a over b times b, and we know that when this happens, we can write it as b over 1 and then cancel the b's out. And so what you get is multiplying the numerators, a over 1, which of course is just a. All right. Now, to illustrate a physics example of this, we're going to use distance. Okay. So the equation for distance traveling for an object moving at constant speed is d is equal to v times t. All right. So let's say, for example, we have an object moving at a speed of 1.5 meters per second for a time of 5 seconds. How much distance is covered in that time period? Well, d is equal to v times t, and so you substitute in for the speed, substitute in for the time. Now you're going to multiply the numbers, 1.5 times time, 1.5 times 5, sorry, and we're also going to multiply the units, meters per second times seconds. Now, of course, the number is 7.5, but now let's multiply the units, and in the same manner as we did up here. Okay, the units follow the same rules of algebra as any other variable. So meters per second times seconds, we're going to write this as seconds over 1, just like we did above. Cancel out the seconds. We get meters over 1, and meters over 1 is just meters. So what we get then is that the distance covered is 7.5 meters. Okay? All right. Okay, another example. Let's convert a length of 75.2 centimeters to meters. All right. Now, 75.2 centimeters is a certain length, about the length of your arm, actually. Now, when we convert it, we don't want to change this length. We just want to write it in different units. Okay. Now, we can do this by multiplying it by 1, because anything multiplied by 1 is itself, right? So we're not going to change anything by multiplying it by 1, but it's going to be a special form of 1, as you'll see. Okay, now the special form of 1 is going to take a form similar to this, x over x, because we know anything over itself is 1. So if we multiply anything by x over x, we're multiplying it actually by 1, and so it's not going to change the original entity. All right. Now, the conversion factor between centimeters and meters is this: 100 centimeters and is equal to 1 meter. Now, it's notable that these two things, 100 centimeters and 1 meter, both represent the same exact length. Okay, so when I write them like this, 1 meter over 100 centimeters, those are the same length, and so they would cancel themselves out just like the x's would up here, and so this would be equal to 1. Okay? All right, stay with me here. All right, so when we convert these things, we are going to need conversion factors, okay, which are, in this case, the same lengths, but written with different units. All right, so here's how we're going to set this up. We're going to put it up like this. We're going to set 75.2 within some parentheses like this, and then we're going to we're going to multiply it by 1. But it's going to be a special form of 1. X over x, 1 meter over 100 centimeters. Okay, since this is a special form of 1, it doesn't change this original length. All right? But what we can do now is to cancel out the centimeters. Okay, because 1 is in the numerator, 1 is in the denominator, and so algebraically they will cancel themselves out, and we'll be left with just meters. That's what we want. Okay? All right, so now we're going to multiply 75.2 times 1, which is 75.2, divided by 100. And then we have the meters. And then working it out to be decimal form, it turns out to be 0.752. All right? So by multiplying the original length by a special form of 1, we don't change the original length, we just write it in a different form. Okay? All right, now I'm going to present a slightly different thing that I like a little bit better. It's called the factor. I don't know why they call it the factor label method, but this is what it's called. You don't have to remember that if you don't want to. But here's the setup for here. Okay, we set up. We just have a line like this, and we put 75.2 centimeters on the top of this line. Okay, now anything above this line is going to represent the numerator, and anything below the line is going to represent a denominator. Okay, and so when I set it up like this, I'm going to put I want to cancel out the centimeters and replace it with meters. So if I take the centimeters, and where am I getting this? I'm getting this from my conversion factor. Okay, I want to cancel out the centimeters, so I put it in the denominator so that it cancels out. Now the only other place for the 1 meter then is in the numerator. It has to go there. There's no other place for it. All right. So note again, I have x over x, and so I'm again multiplying my original length by my special form of 1, and so I don't change the original length, but the centimeters cancel themselves out. Okay, so I get the same thing I had before. Multiply across the numerators, multiply across the denominators, and then do your division. You get the same answer. The reason I like this so-called factor label method, it's a little bit cleaner than, for example, having a slash like that in there when I write it in with parentheses. And you don't have parentheses, you just have, vertical lines, which is, to me, it's a little bit cleaner. So this is going to be my method of choice. Okay, you don't have to do it this way if you don't want to, but I invite you to try it. Okay, you might like it a little bit better too. Okay, as another example of dimensional analysis and conversions, I want to convert a speed. I want to convert 55 miles per hour to feet per second. All right, so you're going down a country road, 55 miles an hour, and for one reason or for whatever reason, we want to convert that to feet per second. Now we're going to so now I'm going to change the problem. Instead of writing it like this, I'm going to write it like this. Or 55 miles per hour is equal to how many feet per second? To do this, we're going to need conversion factors. Now I'm going to have to convert miles to feet, a distance conversion. And if you look up the conversion, it turns out that 1 mile is equal to 5,280 feet. Okay. I'm also going to have to convert hours to seconds. Okay, now I don't know how many seconds there are in an hour, but I know how many minutes there are in an hour, 60. And then I know how many minutes there are how many seconds there are in a minute, right? So we can use these. All right. Okay, so here's how we're going to set it up. I'm going to use the factor label method. I'm going to do 55 miles per hour. Remember, hours in the denominator, per miles per hour. Okay, and I want my goal to get is feet per second. So I want to just do some canceling and stuff so that I get feet in the numerator and only feet, and seconds in the denominator and only seconds. Okay, so I need to convert miles to feet and hours to seconds. Doesn't matter which one you do first. I always do miles to feet first. All right, so now I want to put miles in the denominator because I want to get rid of this mile and I want to replace it with feet. Now actually, I'm not even going to worry about the numbers, 1 and 5,280 and 1 and 60 and all that. I'm not going to worry about the numbers until I know that the units work out. Just because if I make a mistake, it's less to erase. Okay? and it gives me less to look at, so it's easier. So miles are now canceled out, and the only thing left in the numerator is feet, which is good because that's what I want. Now I have to get rid of this hour. Okay, I have to cancel it out. The only way I can cancel it out is to put it in the numerator. Okay, so when I convert from hours to minutes, I'm going to put the hours in the numerator so that they cancel out, and therefore the minutes have to go in the denominator. There's no other place to put them. So now I have minutes in the denominator. I have to convert that to seconds. So I'm going to use my last conversion factor, but I'm going to put the minutes in the numerator again so that they cancel themselves out, and then the seconds go in the denominator. That's the only place for them. Now if you just kind of step back from this problem and take a look at it now, all the units in the numerator are canceled out except for feet. And all the units in the denominator are canceled out except for seconds. So I have what I want, feet per second. Okay? Alright, now I know that's good to go. So now I'm going to put the numbers in. Okay? Now pay attention here because it's easy to make a mistake. 5,280 feet, 1 mile. Okay? 1 hour, 60 minutes. You'd be amazed at how easy it is to flip-flop those. You got to pay attention. 1 minute, 60 seconds. Okay? Alright, now at this point we're going to multiply across the numerators, multiply across the denominators, and then get your calculator out, do a little work, and it turns out to be 81 feet per second. So we've converted 55 miles per hour to feet per second. Okay, next example, 48 meters per second to kilometers per hour. Okay, our conversion factors are meters to kilometers, and again, seconds to hours in this case, so I need these. Okay. All right, now remember, we're starting out 48 meters per second, and our goal is kilometers per hour. Okay, I would invite you to pause this at this point and see if you can place the units in the right place so that the only thing left in the numerator is kilometers, and the only thing left in the denominators is hours. Okay, so I'm going to get rid of the meters, so I want to put them in the denominator. Okay, they cancel. The only place left for the kilometers is the numerator where I want them anyway. Okay, now to get rid of the seconds, I'm going to put them in the numerator, leaving minutes for the denominator. Now to cancel out the minutes, I put them in the numerator, leaving hours for the denominator. Stopping for a moment, checking this out before I go any further. Yep, kilometers in the numerator, hours in the denominator. So far so good. So now I put my numbers in. Again, pay attention to where you make sure that you put them in the right place. It's easy to make a mistake. Okay? And then multiply across the numerators, multiply across the denominator. All right, and do your calculation, and it turns out to be 173 kilometers per hour. 48 meters per second, 173 kilometers per hour. Those are the same speed. Okay, next example. It's very useful. How many square inches are there in a square foot? Okay, now a square foot is the size of a tile on our classroom floor, actually. And I'm just going to represent by this. Okay, and I label it 1 square foot. But I could write this another way, actually. I could write it like this: 1 foot squared. Okay. Now, why do I do it that way? Well, it'll become apparent shortly. All right. Now, a square inch, you can make your, take a moment and make your fingers into 1 square inch of area. Represent 1 square inch of area with your fingers. Okay. I'm going to represent it like this. All right. Okay. Now, the conversion factor between feet and inches, of course, is 1 foot and 12 inches. Those are the same length. Now, you think there are 12 of these in here? If you look at it, I think you'll agree that that wouldn't quite be right, would it? All right. So, how are we going to do this? Well, instead of let's grid this thing off. There's 12 inches this way and 12 inches this way. So I could actually grid this off like this. Okay? And now you could count, 1, 2, 3, 4, 5, 6, or just thinking 12 rows of 12, right? And so how many are there? Well, it's going to be 12 times 12, and that's 144 square inches, right? So you could just draw it out, right? But let's not do it that way. Let's instead use the factor label method. Okay, let's start out like this, and we want to end up with inches squared instead of feet squared. You know? Now we should get 144, right? Well, here's how that happens. Instead of writing foot squared like this, let's write foot squared like this. Foot times foot, right? X times x, x squared, right? X squared, x times x, same thing. Okay, but now, when I use my conversion factor, inches to feet, feet in the denominator, so they cancel out, right? But now, really, I'm only canceling out one of them, okay? I have to do this whole thing again so that I cancel out the other one, okay? So this is only cancel out one dimension, say the x dimension, and then this, the second one, will be canceling out the y dimension. Okay, so we have to cancel out both of them. And that's where you get the 12 times the 12. 12 times 12, inch times inch, 144 square inches. Okay? Okay, one last example. Ice has a density of 0.917 grams per cubic centimeter. Convert to kilograms per cubic meter. A cubic centimeter is actually a unit of volume. Okay? You're going to need two hands for this. Try to make a volume of 1 cubic centimeters. Now, if you don't remember what a centimeter is, it's about the width of your pinky. Okay, so you can try to make a volume of 1 cubic centimeter, and ice within that would have a mass of 0.917 grams. Okay, if it were perfect. Okay, anyway, so to convert this, we're going to need two conversions: grams to kilograms, and cubic centimeters to cubic meters. But that's very difficult to remember. So instead, I'm going to do meters to centimeters. That's a lot easier. 1 meter is 100 centimeters. Okay? So those are conversion factors. Now, we're going to use, we're going to have 0.917 grams per cubic centimeters, remembering the whole time that our goal is kilograms over cubic meters. Okay? Now, I'm going to write, the first thing I'm going to convert is the grams to kilograms. So I'm going to put grams in the denominator and kilograms in the numerator. That way I know that the grams cancel themselves out and I'm left with kilograms. That's what I want. Okay? Now, to convert the cubic centimeters to centimeters, I'm going to write this centimeters cubed, centimeters to the third power, as centimeters times centimeters times centimeters. All right? Now, why do I do that? Because it's easier for me to see that when I'm converting centimeters to meters, I'm putting centimeters in the numerator so that they cancel themselves out. I'm only canceling out one of them, one of the dimension, the x, say, x dimension. I have to do this again to cancel out the y dimension, and then a third time to cancel out the z dimension. Okay, so we have to do this 3 times to cancel out each of the centimeters in the original unit. Okay? Now, stepping back from this a moment, kilograms, and then is the only thing left in the numerator. Meters times meters times meters is cubic meters. And so my units work themselves out. So now I'm going to go ahead and put my numbers in. 1,000 grams for 1 kilogram, and then 100 centimeters for every meter. Okay? And then I'm going to actually get my calculator out and do the calculation. And I invite you to do this as well. The answer that you should get is 917 kilograms per cubic meter. Okay? Dimensional analysis, a very powerful tool in physics.